Right now, as you are listening to this, every single thing in the universe is dying, not in some dramatic, explosive, cinematic way, not in a blaze of glory or a final cosmic collision. The universe is dying the way a cup of coffee goes cold on your desk. Slowly, quietly, and with absolute certainty. In about 100 trillion years, the last star in the universe will use up its final scrap of hydrogen fuel, flicker, and go dark. But that is not the end. That is not even close to the end, because after the last star dies, the universe will continue to exist for a length of time so absurdly, incomprehensibly long that the entire age of stars, every sun that has ever burned, from the very first one that ignited a few 100 million years after the Big Bang to the very last red dwarf sputtering out trillions of years from now. All of that represents less than 1/10 of 1 trillionth 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 of 1% of the universe's total lifespan. The rest is darkness. And what makes this even more unsettling is that this is not some fringe theory. This is not a doomsday prediction from a crackpot with a whiteboard and a YouTube channel. This is the single most widely accepted prediction in all of modern cosmology, backed by 170 years of experimental evidence confirmed by every major physics experiment ever conducted, and supported by cutting-edge observations from instruments that did not even exist 5 years ago. The heat death of the universe is, according to the overwhelming consensus of physicists and cosmologists alive today, how everything ends. But here is the thing that nobody tells you about the end of the universe. The name itself is a lie. Heat death has almost nothing to do with heat. And understanding why that name is misleading, why the most famous prediction in cosmology sounds like the opposite of what it actually describes, is the key to understanding the most terrifying and, strangely, the most beautiful prediction in all of science. So how did we figure out that everything ends in darkness? That story starts not with telescopes or particle accelerators, but with steam engines in 19th century Germany. And it involves a physicist who was so far ahead of his time that the scientific establishment drove him to suicide, only for history to prove him right just months after he died. In 1850, a 30-year-old German physicist named Rudolf Clausius published a paper that would quietly change everything humanity understood about the universe. Clausius was working on a deceptively simple problem. When you burn coal to heat water to make steam to drive a piston, some of the energy always gets wasted. No matter how perfectly you design the engine, no matter how carefully you insulate the boiler, you can never convert all of the heat into useful work. Some of it always leaks away, dissipates, becomes useless. Always. Every single time. Without exception. Now, engineers had known this for decades. They called it a practical limitation, a design challenge, something you could maybe fix if you were clever enough. But Clausius realized it was not a design problem at all. It was a law of nature. And not just any law. It was, in his words, a universal tendency, a cosmic rule that applied not just to steam engines, but to every single process in the entire universe, from the chemical reactions in your body to the nuclear fusion inside stars, to the gravitational collapse of entire galaxies. He spent the next 15 years working out the mathematics, and in 1865, he published the result. He needed a word for this tendency, this one-way flow of energy from useful to useless, from ordered to disordered. He chose the Greek words for in and transformation. He combined them into a single term that would go on to become one of the most important and most misunderstood concepts in all of physics: entropy. Clausius summarized his entire life's work in 2 sentences that hit like a punch to the gut. The energy of the universe is constant. The entropy of the universe tends to a maximum. Read that again. The first sentence says, energy is never created or destroyed. It is always conserved. The total amount of energy in the universe right now is exactly the same as it was at the Big Bang, and exactly the same as it will be a trillion years from now. Nothing is lost. But the second sentence is the killer, because it says that even though energy is always conserved, it is always becoming less useful, more spread out, more disordered, more evenly distributed. And this process only goes in one direction. Entropy increases. It never decreases. The universe is a one-way street toward maximum disorder, and there is no U-turn. But Clausius was not alone in seeing the implications. 13 years earlier, in 1852, a Scottish physicist named William Thomson, who would later become Lord Kelvin, had presented a paper to the Royal Society of Edinburgh with a title that sounds almost clinical, but contained arguably the most terrifying prediction in scientific history: on a universal tendency in nature to the dissipation of mechanical energy. Thomson looked at the same physics Clausius was developing and followed it to its logical conclusion. If energy always dissipates, if useful energy always degrades into useless heat, then eventually, given enough time, all of the energy in the universe would reach the same temperature, the same uniform, useless, lukewarm nothingness. No hot spots, no cold spots, no gradients, no differences. And without differences, nothing can happen. No engines can run, no chemistry can occur, no stars can shine, no life can exist. Thomson called this the heat death of the universe. And the reason the name is so misleading is that heat here does not mean hot. It refers to the science of heat, thermodynamics. The actual temperature of the universe at heat death would be unimaginably cold, just a tiny fraction above absolute zero. The universe does not burn to death. It freezes, it fades, it simply stops. Now, if you are thinking that this sounds depressing, but also kind of abstract, like one of those things physicists worry about that does not really affect your Tuesday afternoon, you are not wrong. The timescales involved are so vast that they make the word incomprehensible feel inadequate. But the physics that drives heat death is not abstract at all. You experience it every single day. Every time you watch ice melt in a glass of water, you are watching entropy increase. The ice is ordered, concentrated cold. The water is disordered, uniform warmth. The ice melts because there are astronomically more ways for water molecules to be arranged as liquid than as a crystal. The most probable outcome wins, always. Think about it this way. Every time you scramble an egg, you are performing an irreversible act. You can unboil an egg, technically, under very specific laboratory conditions, but you cannot unscramble one. There are trillions upon trillions of ways to arrange egg molecules in a scrambled state. There is essentially one way to arrange them in the original, perfect, unbroken yolk and white configuration. Scrambling is easy because disorder is overwhelmingly more likely than order. Unscrambling is impossible because it would require every molecule to spontaneously coordinate all at once by pure chance. The same principle applies to the entire universe. We are all living inside an egg that is in the process of being scrambled, and no one is going to unscramble it. This is also the reason time flows in one direction. The physicist Arthur Eddington gave this concept a name in 1927. He called it the arrow of time, and it is entirely a consequence of entropy. The laws of physics themselves, at the fundamental level, are time symmetric. Run a video of two billiard balls colliding, and it looks perfectly normal, both forward and backward. There is nothing in Newton's laws or Einstein's equations that prefers one direction of time over the other. But in the real world, time obviously has a direction. Eggs break, but do not unbreak. Coffee cools, but does not spontaneously heat up. People age, but do not get younger. And the reason is always the same. The forward direction of time is the direction in which entropy increases. We remember the past because it was lower entropy. We cannot remember the future because it is higher entropy. The arrow of time is, at its core, just the universe rolling downhill toward its most probable state, and the bottom of that hill is heat death. And that is the real insight that took another physicist, one of the most brilliant and tragic figures in scientific history, to fully explain. His name was Ludwig Boltzmann, and his story is one of the saddest in all of science. Boltzmann was born in Vienna on February 20th, 1844, during the dying hours of a Mardi Gras ball. He used to joke that being born between Carnival Tuesday and Ash Wednesday explained his dramatic mood swings, the periods of manic productivity followed by crushing depression. Today, he would almost certainly be diagnosed with bipolar disorder. But Boltzmann's contribution to physics was nothing short of a revelation. He figured out what entropy actually is. At the deepest possible level, Clausius had described entropy as a mathematical quantity. Thomson had predicted its consequences, but Boltzmann explained why it happens, and the answer turned out to be shockingly simple. Disorder is more probable than order. That is it. That is the entire explanation for why the universe is dying. There are vastly, overwhelmingly, incomprehensibly more ways for particles to be arranged in a disordered state than in an ordered one. A shuffled deck of cards can be arranged in any of roughly 8 times 10 to the 67th possible combinations. Only one of those combinations is perfectly ordered, ace through king in each suit. If you shuffle randomly, you will essentially never get a perfectly ordered deck. Not because order is forbidden, not because some law prevents it, simply because disorder is so much more probable that order effectively never happens by chance. Boltzmann expressed this relationship in what many physicists consider the most beautiful equation in all of physics. S equals K log W. Entropy equals Boltzmann's constant times the natural logarithm of the number of possible microscopic arrangements. The equation connects the behavior of trillions of particles to a single number, and it explains why time flows in one direction, why you remember the past but not the future, why eggs break but never unbreak, why the universe is winding down and will never wind back up. But here is where Boltzmann's story turns tragic. Because almost nobody believed him. The scientific establishment of the late 19th century was hostile to Boltzmann's ideas, not because the math was wrong, but because his theory required atoms to be real. And in the 1890s, the existence of atoms was still a matter of fierce debate. Ernst Mach, one of the most influential physicists in Vienna, publicly argued that atoms were nothing more than convenient theoretical fictions. He told Boltzmann, essentially, that he was building his entire career on imaginary objects. Wilhelm Ostwald led an entire movement called energetics that rejected atomism completely. Boltzmann fought back. He debated, he published, he defended his work at conference after conference, but the attacks were relentless, and they took a devastating toll on a man already struggling with his mental health. By 1906, Boltzmann's personal physician reported that the physicist suffered from such severe neurasthenia that he had to abstain from scientific work entirely. Boltzmann lived in constant terror of losing his mind during a lecture. He suffered from asthma, crippling headaches, and eyesight so poor that he could no longer read on his own. On September 5, 1906, while on vacation with his wife Henriette and daughter Elsa at a hotel near Trieste, Ludwig Boltzmann hanged himself from a window casement. His daughter found the body while returning from a swim. And here is the part that makes this story almost unbearable. Just months after Boltzmann's death, a French physicist named Jean-Baptiste Perrin published a series of experiments on Brownian motion that proved definitively and beyond any reasonable doubt that atoms were real. Boltzmann had been right about everything. His equation was correct. His statistical mechanics was correct. His explanation of entropy was correct. He just did not live long enough to see it. Today, if you visit Vienna's Central Cemetery and find Boltzmann's grave, you will see his equation carved into the tombstone. S equals K log W. It is arguably the most famous epitaph in science, and it describes, in 5 symbols, why the universe will end in darkness. But knowing that entropy always increases is one thing. Understanding what that actually looks like on a cosmic scale, over timescales that make the current age of the universe look like a rounding error, that is something else entirely. And to map out exactly how the universe dies, we need to talk about the work of 2 astrophysicists named Fred Adams and Greg Laughlin, who in 1997 published a paper that reads like a horror novel written by someone with a PhD in physics. Adams and Laughlin divided the entire history of the universe, past, present, and future, into 5 distinct ages. And the story they tell is one of the most sobering things you will ever hear. We are currently living in what they called the Stelliferous era, the age of stars. This is the era where nuclear fusion powers stellar interiors, creating light, heat, and the heavy elements that make up everything you have ever touched, tasted, or loved. The universe is about 13.8 billion years old right now, which sounds like a lot until you realize that the Stelliferous era will last for roughly 100 trillion years. We are in the opening credits, the first 1% of 1% of the age of stars. But even this era, as unimaginably long as it is, will end. And it will end because the universe is running out of hydrogen. Stars form when clouds of hydrogen gas collapse under their own gravity, heating up until nuclear fusion ignites in their cores. But the supply of hydrogen is finite. Every star that forms uses up gas that cannot be used again, at least not easily. Massive stars burn through their fuel in just a few million years, while the smallest, dimmest stars, the red dwarfs, are incredibly efficient, burning so slowly that they can last for trillions of years. And this is where red dwarfs become the most important objects in the long-term story of the universe. Red dwarfs make up roughly 75% of all the stars in the Milky Way. They are tiny, dim, and unimpressive by stellar standards. Our Sun is a yellow dwarf, a middleweight star that will exhaust its hydrogen in about 5 billion years, swell into a red giant, swallow Mercury, Venus, and probably Earth, then collapse into a white dwarf the size of the planet it just ate, a dramatic death by any measure. But red dwarfs do not go out like that. They are fully convective, meaning their hydrogen fuel gets continuously mixed throughout the entire star, from core to surface. It is like the difference between a campfire that only burns the logs on top and one that somehow rotates every log through the flame. Red dwarfs use nearly 100% of their hydrogen. The smallest ones, those with about 8% the mass of the Sun, can burn for over 10 trillion years. Think about that for a second. The universe is 13.8 billion years old. The smallest red dwarfs can burn for 10 trillion years. That means the last red dwarf will not die until the universe is roughly 700 times its current age. These tiny, unremarkable little stars will outlast everything else. Every galaxy, every nebula, every supernova remnant. Long after every star you can see in the night sky has gone dark. Long after the Sun is a frozen cinder. Long after the Milky Way and Andromeda have collided and merged into a single bloated galaxy. Some nameless red dwarf in some forgotten corner of that merged galaxy will still be burning. The last candle in a very large room. And here is something strange to consider. In about 2 trillion years, the expansion of the universe will have carried every galaxy beyond our local group past the cosmic horizon. They will be moving away from us faster than their light can ever reach us. An astronomer born in that far future would look up at the sky and see only the local group's merged supergalaxy. They would have no evidence that the broader universe ever contained billions of other galaxies. No evidence of the cosmic microwave background, redshifted to undetectable wavelengths. No evidence of the Big Bang itself. They would live in what appears to be a single galaxy in an infinite void, and they would have no way of knowing that the universe was ever any different. The physicist Lawrence Krauss and cosmologist Robert Scherer pointed this out in a 2007 paper that reads like a cosmic horror story disguised as astrophysics. The evidence for our current understanding of cosmology, including the Big Bang, the expansion of the universe, and the existence of dark energy, will be erased by the very processes those discoveries describe. The universe will not just die, it will destroy the evidence that it ever lived, but eventually, even the red dwarfs will die. And when the last one flickers out, the Stelliferous era ends. The universe goes dark. Not metaphorically, literally. If you were somehow floating in space at that moment, you would see nothing. No stars, no glow, no distant galaxies twinkling on the horizon. Just blackness. And not the temporary blackness of night where you know dawn is coming. Permanent blackness. The blackness of a universe that will never produce another photon of starlight. And this is where most people assume the story ends. Stars die, lights go out, credits roll. But the universe does not end when the last star dies. It does not even come close to ending. Because what follows the Stelliferous era is a series of ages so long and so strange that the entire age of stars, all 100 trillion years of it, becomes a footnote. Adams and Laughlin called the next phase the degenerate era, and it lasts from about 10 to the 15th power years to 10 to the 39th power years after the Big Bang. The name comes from degenerate matter, the exotic form of matter that makes up stellar corpses, white dwarfs, neutron stars, and black holes. These are the objects that populate a starless universe. White dwarfs are the remnants of stars like our Sun. After a medium-sized star exhausts its hydrogen, expands into a red giant, and sheds its outer layers. The core that remains is a white dwarf. It is about the size of Earth, but with the mass of the Sun. A teaspoon of white dwarf material weighs about 15 tons. And white dwarfs have no internal energy source. They do not fuse anything. They just sit there, radiating the residual heat from their formation, getting slowly, imperceptibly cooler. After about 10 to the 15th power years, roughly a quadrillion years, white dwarfs cool to about 5 degrees above absolute zero. At that point, they become something that does not yet exist anywhere in the universe, something that cannot exist yet because the universe is far too young. They become black dwarfs, cold, dark, dead spheres of crystallized carbon and oxygen, invisible against the blackness of space. No light, no heat, nothing, just mass, sitting in the void. But the degenerate era is not completely dark. Very rarely, once every few quadrillion years or so per galaxy, two white dwarfs drifting through the darkness will find each other, spiral inward, and collide. And for a few glorious weeks, a Type 1a supernova lights up the void, briefly outshining a billion stars that no longer exist. Then it fades, and the darkness returns. Even more rarely, two brown dwarfs, failed stars that never quite ignited nuclear fusion in the first place, might collide and merge into a single object massive enough to start fusing hydrogen, a new star born not from a collapsing gas cloud, but from the random collision of stellar rejects. It would burn for trillions of years in absolute solitude, the only point of light in an observable universe of total darkness. But the odds of this happening grow smaller and smaller as the universe expands and objects drift further apart. Eventually, these cosmic accidents stop entirely. And then there is the question that might determine how the degenerate era ends. A question that physicists have been trying to answer for decades with increasingly elaborate experiments. Two protons decay. This matters enormously because protons are what matter is made of. Every atom in your body, every atom in every white dwarf and neutron star and rogue planet drifting through the dark is built from protons, neutrons, and electrons. Neutrons decay on their own in about 15 minutes when they are not bound inside an atom. But protons appear to be stable. No one has ever observed a proton decay. However, several grand unified theories in particle physics predict that protons are not truly stable. They just have incredibly long half-lives. The Super Kamiokande experiment in Japan, which is basically a giant tank containing 50,000 tons of ultra-pure water buried deep underground, surrounded by 11,000 photomultiplier tubes waiting to catch the faintest possible flash of light from a decaying proton, has been running for decades, and it has seen nothing. As of 2020, Super K has established that the proton's half-life must be greater than 10 to the 34th power years. That is 1 followed by 34 zeros, a number so large that If you started counting at the Big Bang, you would not even be a rounding error by the time you reached it. But greater than does not mean infinite. Many physicists still believe protons will eventually decay, just on timescales that make our experiments look laughably short. If protons do decay, then sometime between 10 to the 34th and 10 to the 41st power years from now, every piece of matter in the universe will slowly, atom by atom, evaporate into positrons and gamma rays, white dwarfs, neutron stars, rogue planets, all of it, gone, not exploded, not collapsed, just quietly dissolved by the fundamental instability of the particles they are made of. A white dwarf undergoing proton decay would generate about 400 watts of power, roughly enough to run a few light bulbs. That is what the death of a star-sized object looks like when stretched over timescales that make the age of the universe look like a heartbeat. But whether or not protons decay, the universe still has one more act to play, because even after all baryonic matter has either decayed or been swallowed, one type of object remains. The most extreme, most alien, most terrifyingly patient objects in all of physics. Black holes. In the degenerate era, black holes are cosmic vacuum cleaners, slowly accumulating matter through random gravitational encounters. A white dwarf drifts too close, gets torn apart, absorbed. A neutron star wanders into range, spirals in, disappears behind the event horizon. Over incomprehensible timescales, stellar mass black holes grow, and the supermassive black holes at the centers of dead galaxies, monsters containing billions of solar masses, sit and wait in the darkness like ancient gods. For a long time, physicists assumed black holes were eternal. Once something crossed the event horizon, it was gone forever. The black hole only grew. It never shrank. It was the ultimate endpoint, the final resting place of matter and energy. And then Stephen Hawking ruined everything. Actually, the story starts slightly before Hawking, with a graduate student named Jacob Bekenstein. In 1972, Bekenstein was working on his PhD at Princeton under the supervision of John Wheeler, the same John Wheeler who coined the term black hole. Bekenstein had a radical idea. He proposed that black holes have entropy, and that this entropy is proportional to the surface area of the event horizon, not the volume. This was shocking because it meant black holes are not simple objects. They are thermodynamic systems with temperature and entropy just like anything else. The physics community initially rejected this. Hawking himself was irritated by the claim. If black holes have entropy, they must have temperature. And if they have temperature, they must radiate. But nothing can escape a black hole. So Bekenstein had to be wrong. Except Hawking set out to disprove Bekenstein, and accidentally proved him right. In 1974, Hawking published a paper that might be the single most important prediction in theoretical physics since Einstein. Working at the intersection of quantum mechanics and general relativity, Hawking showed that black holes are not truly black. They glow, very, very faintly. They emit thermal radiation, now called Hawking radiation, and this radiation carries energy away from the black hole, causing it to slowly lose mass. The mechanism is subtle and often badly explained. The popular version involves pairs of virtual particles popping into existence near the event horizon, with one particle falling in and the other escaping. Hawking himself acknowledged that this explanation is an oversimplification, bordering on misleading. The actual physics involves the way quantum vacuum states behave differently in curved spacetime near a black hole's event horizon compared to flat spacetime far away. But the result is the same. Black holes radiate, they lose mass, and given enough time, they evaporate completely. But here is the twist that makes it even stranger. The rate of evaporation depends on the black hole's mass, and the relationship is inverted. Smaller black holes are hotter and evaporate faster. Larger black holes are cooler and evaporate slower. A black hole with the mass of the Sun would have a temperature of about 60 billionths of a degree above absolute zero and would take approximately 10 to the 67th power years to evaporate. That is already a number so large that the entire Stelliferous era, all 100 trillion years of star formation and stellar death, is nothing compared to it. But the supermassive black holes, the ones with billions of solar masses, are even colder and even more patient. The largest ones will take roughly 10 to the 100th power years to evaporate. That number has a name. It is called a googol, one followed by 100 zeros, and it represents, as far as our best physics can determine, the approximate expiration date of the last significant structure in the universe. When the last supermassive black hole finally evaporates, it does not go quietly. In its final moments, as its mass decreases, its temperature rises. It gets hotter and hotter, radiating more and more intensely, until in its last fraction of a second, it explodes in a burst of gamma radiation. One final flash of light in a universe that has been dark for longer than any human mind can conceive, and then it is gone. But the death of the last black hole raises one of the deepest unresolved questions in physics, the information paradox. When stuff falls into a black hole, what happens to the information about what that stuff was? Quantum mechanics requires that information is never truly destroyed. It can be scrambled, rearranged, encoded in a form you cannot read, but it cannot be erased. Yet Hawking radiation appears to be purely thermal, like the glow from a hot poker. It carries no information about what fell in. So when the black hole evaporates completely, where did the information go? Hawking argued for decades that the information was simply lost, destroyed, gone. This horrified most physicists because it violated a fundamental principle of quantum mechanics called unitarity. Don Page showed in 1993 that if evaporation preserves information, the entropy of the radiation must follow a specific curve, rising at first and then falling back to zero by the time the black hole disappears. Hawking's calculation predicted it would rise forever. One of them had to be wrong. Major breakthroughs in 2019 and 2020 involving calculations of something called entanglement islands, regions inside the black hole that are somehow encoded in the external radiation, showed that Page was right. The information is preserved. Somehow. The precise mechanism remains mysterious. As physicist Raphael Bousso put it, we now can compute the correct answer, but we still do not fully understand why it is correct. The universe keeps its secrets even as it reveals its fate. And that is when the real darkness begins. Adams and Laughlin called this final phase the Dark Era. And it is not an era in any meaningful sense. It is eternity. The universe at this point contains nothing but a thin, impossibly dilute gas of photons, electrons, positrons, and neutrinos, all drifting through an ever-expanding void. No structures, no gradients, no temperature differences, no possibility of work, chemistry, computation, or life. Entropy has reached its maximum. The universe is in thermodynamic equilibrium, and in equilibrium, by definition, nothing happens. Occasionally, an electron and a positron drifting through the void will find each other and briefly form a positronium atom, a strange and unstable little bound state that orbits for a while before the two particles annihilate each other and release a pair of photons. This is among the last events that can occur, and even these become rarer and rarer as the universe expands and particles drift further apart. If you could somehow be there to observe it, the dark era would be the loneliest thing imaginable. Imagine floating in a void so vast that the nearest other particle is further away and the current observable universe is wide. No stars anywhere, in any direction, at any distance. No light to see by, no warmth to feel. A temperature of approximately 10 to the minus 30 degrees above absolute zero. Effectively, nothing. And this nothing stretches in every direction, without boundary, without variation, without end. Not for 1 billion years, not for 1 trillion. Forever, this is where everything that has ever existed, every galaxy, every star, every planet, every person, every thought, every symphony, every war, every act of love or cruelty that has ever occurred in the entire history of the cosmos. This is where it all leads. An empty room that nobody will ever enter or leave. The temperature of the universe at this point is so close to absolute zero that it barely registers. The photons, stretched to absurdly long wavelengths by the expansion of space, carry almost no energy. The particles are so far apart that they might as well be in separate universes. And this state, this cold, dark, empty, changeless nothing, is what the universe looks like for the rest of eternity. But wait, how do we know the universe will actually keep expanding forever? How do we know gravity will not eventually pull everything back together? How do we know there is not some mechanism, some escape hatch, some cosmic loophole that could save us from this fate? That question was answered, emphatically and depressingly, in 1998. And the answer came from 2 teams of astronomers who were not even looking for it. Saul Perlmutter at the Lawrence Berkeley National Laboratory led a group called the Supernova Cosmology Project. Brian Schmidt at the Australian National University and Adam Rees at Johns Hopkins led a rival team called the High Z Supernova Search Team. Both groups were measuring the expansion rate of the universe using Type 1 as supernovae as cosmic distance markers. These supernovae all explode with roughly the same brightness, which makes them useful as standard candles. If you know how bright something actually is, and you measure how bright it appears, you can calculate how far away it is. Both teams expected to find that the universe's expansion was slowing down. That was the prevailing assumption. Gravity should be pulling everything back together, decelerating the expansion that began with the Big Bang. The only question was how fast it was decelerating, which would tell you whether the universe would eventually stop expanding and collapse, or expand forever but progressively slower. What they found instead was something nobody anticipated. The supernovae were dimmer than expected, not brighter, dimmer, which meant they were farther away than they should have been, which meant the universe was not decelerating at all. It was accelerating. Both teams checked their data obsessively. They looked for errors. They recalibrated their instruments. They wondered if cosmic dust was dimming the supernovae. They considered whether Type 1 supernovae might have been different in the distant past. Nothing explained it. The signal persisted. And when both teams, working independently and in direct competition with each other, arrived at the same result, the physics community realized this was not a mistake. It was a discovery, one that upended everything cosmologists thought they knew about the fate of the universe. The expansion of the universe is speeding up. Galaxies are flying apart faster and faster and faster, driven by something that nobody fully understands, something that makes up about 68% of the total energy content of the universe, something that physicists, in one of the great shrugs of modern science, decided to call dark energy. This discovery won Perlmutter, Schmidt, and Rees the Nobel Prize in Physics in 2011, and it effectively sealed the universe's fate. Because if the expansion is accelerating, then the universe will never collapse. There will be no big crunch. Galaxies will never fall back together. Instead, they will be carried further and further apart until every galaxy beyond our local group has receded past our cosmic horizon, moving away from us faster than the speed of light, not because they are moving through space faster than light, but because space itself is expanding between us faster than light can cross it. In about 2 trillion years, an astronomer living in what used to be the Milky Way will look out at the sky and see nothing, no distant galaxies, no evidence that the universe ever contained anything beyond their local cluster of stars. The rest of the cosmos will have been carried beyond the observable universe, lost forever. And this is where the story took its most recent and possibly most interesting turn. Because in 2024 and 2025, a new instrument started delivering data that suggests dark energy might be even stranger than we thought. The Dark Energy Spectroscopic Instrument, or DESI, is mounted on a telescope at Kitt Peak in Arizona. It has spent 3 years mapping the 3-dimensional positions of roughly 15 million galaxies and quasars, creating the most detailed map of the universe's large-scale structure ever assembled. And when scientists analyzed the second data release in March 2025, they found something unexpected. Dark energy might not be constant. The standard model treats dark energy as a cosmological constant, a fixed property of empty space that never changes. Albert Einstein originally introduced this concept in 1917 to keep his equations from predicting an expanding universe, which he found philosophically unacceptable. He later called it his biggest blunder, but the 1998 discovery brought it back. And for 25 years, the cosmological constant seemed to fit the data perfectly. DESI's results suggest otherwise. The data show a preference for dark energy that was stronger in the past and has been getting weaker over time. The statistical significance ranges from about 2.8 to 4.2 sigma, depending on what other data you combine it with. Dr. Mustafa Ishaq Boushaki at UT Dallas put it bluntly. With 4.2 sigma significance, he said, "We are getting to the point of no return." Now, 4.2 sigma is not 5 sigma, which is the threshold physicists traditionally require to claim a discovery. So, this is not confirmed yet, but if it holds up, it means dark energy is not a simple constant, but something more dynamic. possibly what theorists call quintessence, a field that evolves over time. The Dark Energy Survey independently found similar anomalies in its 2025 legacy results, adding weight to the case. But here is the critical question. Does evolving dark energy change the universe's fate? Could it somehow rescue us from heat death? Probably not. Even in models where dark energy weakens over time, the universe still expands indefinitely. The expansion might slow compared to the cosmological constant scenario, but it does not reverse. Heat death still wins. It might just take a little longer. However, there are other ways the universe could end, and some of them are significantly more dramatic than slowly fading to black. The Big Crunch is the classic alternative. If the universe contained enough mass, gravity could eventually halt the expansion and pull everything back together into a single point. A reverse Big Bang. Background radiation would heat up until about 100,000 years before the final crunch. It would become hotter than the surfaces of stars. Everything would be incinerated long before the final collapse. The problem with the Big Crunch is that the universe does not contain nearly enough matter. You would need roughly 17 times more mass than we observe, and dark energy is actively pushing things apart. Under standard physics, the Big Crunch is effectively ruled out. That said, there is a provocative paper from Henry Tai at Cornell, published in October 2025, suggesting that DESI and DES data could indicate a negative cosmological constant at late times, which could theoretically lead to a Big Crunch about 20 billion years from now. This is highly speculative, and most cosmologists are skeptical. But it is worth mentioning because science occasionally overturns its own consensus, and a healthy dose of humility is warranted when predicting the behavior of something that makes up 68% of the universe and that nobody understands. Then there is the Big Rip. In 2003, physicist Robert Caldwell at Dartmouth, along with Mark Kamienkowski and Neven Weinberg, proposed a scenario where dark energy does not just stay constant or weaken. It gets stronger over time. They called this phantom energy. And if it is real, the consequences are apocalyptic. In a Big Rip scenario, the accelerating expansion eventually becomes so powerful that it overwhelms every other force in the universe. First, galaxy clusters are pulled apart. Then, individual galaxies disintegrate. Then solar systems are ripped apart. Then planets explode. Then atoms are torn apart. Then atomic nuclei are shredded. Everything, down to the subatomic level, is ripped to pieces by the expansion of space itself. Caldwell calculated that for a particular value of the dark energy equation of state, the Big Rip would occur about 22 billion years from now. In the final moments, Earth would explode about 30 minutes before the end. Fortunately, DESI data suggest the opposite of phantom energy. Dark energy appears to be weakening, not strengthening. The Big Rip is possible, but currently unsupported by observations. And then there is the genuinely terrifying one, vacuum decay. When physicists measured the mass of the Higgs boson at the Large Hadron Collider in 2012, they got a number that landed in an uncomfortable zone. The Higgs mass, roughly 125.1 billion electron volts, combined with the top quark mass, suggests that our universe might be sitting in what physicists call a false vacuum. Think of it like a ball resting in a small dip partway up a hill. The ball looks stable. It is not rolling anywhere. But it is not at the bottom of the hill. There is a lower energy state available. And if the ball gets nudged, or if it spontaneously quantum tunnels through the barrier, it will roll down to the true bottom. If our vacuum is false, a bubble of true vacuum could nucleate somewhere in the universe through random quantum fluctuation. This bubble would expand at nearly the speed of light, rewriting the laws of physics as it goes. Inside the bubble, the fundamental constants would be different. Different particle masses, different forces, different chemistry. No atoms as we know them, no molecules, no anything resembling the universe we inhabit. Everything inside the bubble would be reorganized according to entirely new physics, physics that may not permit any form of complexity or structure or life, and you would never see it coming. The bubble approaches at essentially the speed of light, so the first warning would also be the last. One moment you exist, the next moment the region of space you occupied has been overwritten. You would not even have time to realize something had gone wrong. It would simply be as if you had never existed at all, because in the new physics of the bubble, you could not have existed. Sidney Coleman and Frank DeLucia analyzed this possibility back in 1980. Their conclusion was, in their words, disheartening. The bubble interior would undergo immediate gravitational collapse. But here is the good news, if you can call it that. The calculated lifetime of our vacuum, even if it is false, appears to be many orders of magnitude longer than the current age of the universe. And the fact that the enormous energies of cosmic inflation, far higher than anything the Large Hadron Collider can produce, did not trigger vacuum decay is a strong argument that either we are in a true vacuum or something stabilizes us that we do not yet understand. So vacuum decay is possible in principle, but probably not imminent. Of all the alternatives, heat death remains the most likely. It is the default ending, the one that does not require anything exotic or unlikely to happen. It just requires the universe to keep doing what it is already doing, expanding, cooling, spreading its energy ever more thinly across an ever larger volume of space. It is the most boring apocalypse imaginable, and that is exactly why physicists believe it. But the heat death timeline contains one more twist, one more deeply strange implication that emerges from the intersection of thermodynamics and infinity, and it involves the most disturbing thought experiment in modern physics, Boltzmann brains. Remember Boltzmann's insight. Entropy increases because disordered states are more probable than ordered ones. But Boltzmann himself realized something unsettling about this. If the universe exists for infinite time in a state of maximum entropy, then given infinite time, random thermal fluctuations will occasionally, purely by chance, produce any possible configuration of matter, including a functioning human brain, complete with false memories of having evolved on a planet in a universe full of stars. These hypothetical entities are called Boltzmann brains, a term coined by physicists Andreas Albrecht and Lorenzo Sorbo in 2004, though the underlying idea goes back to Boltzmann himself, who in 1896 speculated that our entire observable universe might be nothing more than an extraordinarily rare fluctuation in an otherwise featureless sea of maximum entropy. Boltzmann suggested that we exist not because the universe began in a low entropy state, but because random chance occasionally creates pockets of order. The modern version of this idea is even more disturbing. Because here is the issue. Over infinite time, the number of Boltzmann brains randomly fluctuating into existence in a state of maximum entropy would vastly outnumber the number of real observers who evolved naturally in the Stelliferous era, by a ratio so large it makes the number of atoms in the observable universe look like nothing. If you are just a random observer, statistically speaking, you should almost certainly be a Boltzmann brain. The fact that you appear not to be, the fact that you experience a coherent universe consistent with actual cosmic evolution rather than a jumble of random impressions, is paradoxical. Several solutions have been proposed. One is that the universe will undergo vacuum decay before Boltzmann brains have time to dominate, essentially pulling the plug on infinity. Another invokes certain interpretations of quantum mechanics that prevent random fluctuations from producing coherent, conscious experiences. The problem remains unsolved, but it illustrates just how weird things get when you follow the physics of heat, death, to its logical conclusions. There is also the Poincare recurrence theorem, which states that any finite system governed by reversible dynamics will eventually return arbitrarily close to its initial state. In principle, given enough time, the universe could cycle back to something resembling its current configuration. Physicist Don Page calculated the recurrence time for a universe scale system at roughly 10 to the 10 to the 10 to the 56th power years. Write that number out and you would need more digits than there are atoms in the observable universe. Compared to Poincare recurrence, the Google year evaporation time of supermassive black holes is essentially instantaneous. And crucially, our accelerating universe may not satisfy the theorem's requirements anyway, since it is unclear whether an ever-expanding cosmos has a finite phase space. So, is there any hope? Is there any scenario where life, intelligence, consciousness could survive heat death? Freeman Dyson thought so. In 1979, the legendary physicist published a paper called Time Without End, Physics and Biology in an Open Universe. It was written as a direct response to Steven Weinberg's famous and deeply gloomy statement that the more the universe seems comprehensible, the more it also seems pointless. Dyson's retort was characteristically defiant. No universe with intelligence is pointless. Dyson argued that intelligent beings could survive indefinitely in a cooling universe by being smart about energy conservation. The key was a result from information theory called Landauer's principle, which establishes a minimum energy cost for processing a single bit of information. That minimum cost is proportional to the ambient temperature. As the universe cools, computation gets cheaper. So Dyson proposed a strategy. Store a finite amount of energy. Use half of it to power your thoughts. When that half is exhausted, enter hibernation. While you sleep, the universe cools further, and the minimum energy cost of thinking decreases. So when you wake up, use half of what remains, then hibernate again, and so on, forever. Like a mathematical limit, you approach zero, but never reach it. You think increasingly slowly in cosmic time, but your subjective experience remains constant. From your perspective, you never run out of time. The math worked beautifully. Dyson showed that by carefully timing hibernation and computation periods, an intelligent being could perform an infinite number of thoughts using finite energy. The catch was that each thought would take longer and longer in absolute time. toward the end. A single thought might take longer than the current age of the universe. But from the perspective of the thinker, time would feel normal. You would never notice the gaps. You would simply think, sleep, forever. It was consciousness reduced to its mathematical minimum, stripped of everything physical and material, but still somehow persisting. It is an elegant, almost poetic idea. Consciousness surfing the curve of entropy toward infinity, forever adapting, forever slowing down, but never stopping. But Dyson himself later acknowledged a fatal problem. His 1979 paper assumed a universe that was expanding linearly, decelerating over time. In a universe dominated by a cosmological constant where expansion accelerates, the math changes. The cosmic horizon shrinks over time, cutting you off from energy sources, and the background temperature approaches a fixed minimum, the de-Sitter temperature, rather than falling to zero. This means the Landauer trick does not work. There is a minimum energy cost per computation that never decreases, and eventually your finite energy supply runs out. When asked about this later, Dyson was honest. His paper was, in his words, obsolete in light of the accelerating expansion. Even the most optimistic scenario for life's long-term survival appears to have been killed by dark energy, which leaves us with a question that is less about physics and more about philosophy. What does it mean if everything ends? Humans have been grappling with this question long before physicists formalized it in equations. Nearly every civilization in history has had a story about how the universe ends, and some of them came remarkably close to the scientific picture. In Hindu cosmology, the universe undergoes vast cycles of creation, preservation, and destruction. Brahma creates, Vishnu preserves, Shiva destroys. And the timescales involved are staggering. A single day of Brahma lasts 4.32 billion years. His complete lifespan is 311.04 trillion years. These numbers, imagined thousands of years before modern astronomy, are eerily close to the scientific timescales for stellar lifetimes. But unlike heat death, the Hindu cycles always begin again. Destruction is followed by creation. There is no final ending. Norse mythology took a different approach. Ragnarok, the twilight of the gods, describes the end of the world in fire and flood. Gods and monsters destroy each other. The sun is swallowed by a wolf. The world sinks into the sea. But then, from the waters, a new world rises. 2 surviving humans repopulate the earth. The Norse did not flinch from the inevitability of destruction. Instead, they found meaning in how you face it. The gods know Ragnarok is coming. They fight anyway, because the point is not to win. The point is to be worthy of the story. Buddhist cosmology describes infinite cycles without beginning, without creator, without endpoint. Universes arise from conditions, pass through phases of formation, abiding, destruction, and emptiness. Then the cycle repeats. But the truly important insight of Buddhism is not about the cosmic cycle at all. It is about escaping it. Individual liberation, nirvana, transcends the cycle entirely. The goal is not to survive the end of the universe. It is to transcend the need for a universe at all. There is something deeply human about the fact that every culture looked at the night sky and asked the same question: how does it end? And there is something remarkable about the fact that our species eventually built instruments precise enough to answer it. The science fiction writer Isaac Asimov wrestled with this question more brilliantly than almost anyone. His 1956 short story, The Last Question, was, by his own frequent admission, his favorite of all the stories he ever wrote. It spans the entire future history of humanity across 7 vignettes, from the near future to the far, far, far future. And in each one, someone asks a computer of increasing sophistication the same question. Can entropy be reversed? Can the running down of the universe be stopped? Each time, across millennia, across eons, across ages where humanity has merged with its technology and transcended physical form entirely, the answer comes back the same. Insufficient data for meaningful answer. Finally, after heat death, after all stars have died and all matter has decayed, and even the last photons have redshifted to nothing, only the cosmic computer remains, existing in hyperspace, still processing the question. And after an unspecified eternity of computation, it finds the answer. But there is no one left to tell. Asimov's ending is one of the most famous in all of science fiction. The computer, having finally solved the problem of entropy, implements the solution. Let there be light, it says. And there was light. Heat death becomes the Big Bang of a new universe. Physics becomes theology. Entropy becomes creation. It is a beautiful story, and it is almost certainly wrong. There is no known mechanism by which entropy can be globally reversed. There is no computer, no intelligence, no process that can decrease the total entropy of a closed system. The second law of thermodynamics is not a suggestion. It is not a guideline. It is a law in the deepest sense of the word, a statistical certainty that emerges from the most fundamental mathematics of probability. Disorder wins because disorder is overwhelmingly more probable than order, and no amount of intelligence or computation can change the odds. But there is another way to think about it, a way that does not require reversing entropy or cheating physics or invoking science fiction deus ex machina. Roger Penrose, the Nobel laureate mathematician and physicist, proposed something called conformal cyclic cosmology. His idea is strange and elegant. At the end of our universe, when everything has decayed and only massless particles like photons remain, something interesting happens to the geometry of space-time. Photons do not experience time. From a photon's perspective, it is created and absorbed in the same instant, regardless of how far it travels. Whether a photon crosses a room or crosses the entire observable universe, its experience of elapsed time is exactly 0. This is not a metaphor. It is a direct consequence of special relativity. At the speed of light, time stops. In a universe where only photons exist, the concepts of distance and time become meaningless. There are no clocks, because clocks require massive particles. There are no rulers, because rulers require matter. An infinitely large, cold, empty universe becomes mathematically equivalent through what mathematicians call a conformal transformation to an infinitely small, hot, dense point. The transformation preserves the angles and relationships between things, but rescales all the distances. And the rescaled version of heat death looks exactly like the Big Bang. In other words, the end of one universe looks exactly like the beginning of the next. Penrose calls each cycle an aeon. He has spent years searching for observational evidence, claiming to find circular temperature anomalies in the cosmic microwave background that he interprets as Hawking points, the signatures of supermassive black hole evaporation events leaking through from a previous ion. Multiple independent analyses have disputed these findings, arguing that similar patterns appear naturally in standard inflationary models. The evidence at this point is not convincing. But the idea remains one of the most creative and profound attempts to find meaning in the heat death of the universe. And maybe that is the real takeaway from all of this. Not the timeline, not the physics, not the mind-numbing numbers, but the fact that human beings, creatures made of atoms that will eventually decay, living on a planet that will eventually be consumed, orbiting a star that will eventually die, in a universe that will eventually go dark, have spent centuries trying to understand and even overcome the ending. Clausius lost his wife and raised 6 children alone, while continuing to refine his thermodynamic equations. He was wounded in the Franco-Prussian War while running an ambulance corps with his students. He kept working through all of it. Boltzmann, driven to despair by a scientific establishment that refused to accept the truth he could see so clearly, carved his legacy into an equation and left it for the future to validate. Hawking, told at 21 that he had 2 years to live, survived for another 55 years, and in that time showed us that even black holes, the most extreme objects in the universe, are temporary. When he died in 2018, they buried his ashes in Westminster Abbey between Darwin and Newton. His tombstone bears his most famous equation, the one for the temperature of Hawking radiation. Beside it are the words, "Here lies what was mortal of Stephen Hawking." Even the inscription acknowledges the temporary nature of physical existence. Freeman Dyson, confronted with the apparent pointlessness of a dying cosmos, simply refused to accept it and started doing math. These were not people paralyzed by the darkness at the end of the timeline. These were people who saw the darkness and decided to light something anyway. And there is a deep irony embedded in the heat-death prediction itself. The very same physics that guarantees the universe will end in darkness is the same physics that made the universe interesting in the first place. Entropy is why ice melts, but it is also why the sun shines. Stars are entropy machines. They take concentrated nuclear fuel and convert it into diffuse light and heat, increasing the entropy of the universe with every photon they emit. Life itself is an entropy-generating process. You eat ordered food, break it down, and radiate disordered heat. The price of existence is entropy, and the bill eventually comes due. But not yet. Right now, the universe is 13.8 billion years old. Stars will continue to form for another 100 trillion years. The smallest red dwarfs will burn for 10 trillion more after that. Even after the last star dies, black holes will persist for a Google years. We are not at the end. We are not even at the beginning of the end. We are at the end of the beginning. The Stelliferous era, this brief cosmic spring where stars blaze and planets form and chemistry happens and life evolves and organisms look up at the night sky and wonder what it all means. This era is a flash, a blink, a fleeting heartbeat in the life of a universe that will spend almost all of its existence in cold, dark silence. Every sunset you have ever watched, every star you have ever seen, every moment of warmth and light and energy that has ever existed, all of it occupies an almost immeasurably tiny fraction of cosmic time. And somehow, here you are, made of atoms forged in the cores of dead stars, powered by a nuclear reactor 93 million miles away, hearing these words during the one brief epoch when any of this is possible. You are a temporary arrangement of matter that has learned to contemplate its own impermanence. And that is, when you really think about it, the most extraordinary thing that entropy has ever produced. The universe will end in darkness. The physics is clear. The math is settled. The second law will not be denied. But for now, the stars are burning. And that means something. Not because the universe cares, but because we are here to notice. And noticing is itself a kind of defiance. Entropy says everything runs down. Consciousness says yes, but not before I understand why. Boltzmann's tombstone reads S equals K log W. But maybe the real equation of the universe is simpler than that. Maybe it is just this. Everything ends, everything fades, everything runs down, but not yet. And not yet is all any of us have ever had. If you want to see what happens when the universe is not just dying but might be too perfectly designed, check out our video on the simulation theory. It is on screen right now. And if you made it this far, you are clearly someone who actually cares about understanding the big questions. So subscribe. I will see you in the next one.